And as I mentioned, flip-flops with different control sets cannot be packed into the same slice. So in this example, we see 3 flip-flops resynthesized to force some control signals to associated LED inputs so that these registers can be packed into the same slice. There are 3 ways to get the FPGA resources you need into your design. You can either infer logic with your synthesis tool, instantiate primitives from the Xilinx Unified Library, or instantiate an optimized component from the core generator. One of the biggest challenges for new users is to make certain that they are inferring the appropriate resources. First of all, one of the best ways to check that you are getting the resources inferred is to check the schematic viewer from your synthesis tool. All of the high-end synthesis tools have schematic viewers. The viewers are used to graphically display a gate-level version of your netlist and also a technology view of your netlist. While a gate-level netlist is worthwhile to check the Boolean optimization produced by your synthesis tool, the technology view helps you understand what Xilinx primitives were inferred by your synthesis tool or what primitives were not inferred by your synthesis tool. A primitive is a resource that is written to the netlist that represents a particular FPGA resource, such as a LUT, shift register LUT, or distributor RAM. Xilinx provides a library of primitives called the Xilinx Unified Library to all of our synthesis partners and customers so that they can create netlists that are optimal for their customer's design. Well, this same library is available to anyone who wants to instantiate a primitive into your FPGA. So if you're ever trying to work around what your synthesis tool won't do, you can always go here to the Xilinx Unified Library and instantiate the component. The core generator and the architecture wizards make larger optimized components available to you. While some cores have a charge associated with them, most do not. The cores range from simple components to large, highly complex IP. The architecture wizard is used most commonly to customize DCM and PLL components. All primary slice resources can be inferred by XST and Simplify. This includes LUTs, flip-flops, the shift register LUT muxes, and carry logic. However, you must be sure to code for the resources properly. This means that if you define a flip-flop with an incompatible combination of control signals, you may get something slightly different, maybe a LUT input used for a control signal. Likewise, the shift register LUT is non-loadable, has no reset, and only supports a serial functionality. So if you code for a parallel read, you will get a pure register implementation, and this may not be what you expected. Similarly, muxes should use a case statement, and carry logic should use the proper arithmetic operator. Don't code for the XOR functionality and expect it to target the carry logic resource. In general, Inference is best and preferred by our customers. It assures portability to another technology and is, of course, reusable. However, most customers will have to do some instantiation of the design to get all the dedicated hardware they need. A list of Xilinx primitives and their behavior can be found from the Libraries Guide for your chosen device family. This is available at support.xilinx.com or can be found from the Help menu from the ISE software. This will describe all the ports and attributes that can be customized. There is also a complete description of the XST attributes located from the software manual webpage. This is always a useful resource for inferring logic. The core generator and architecture wizards help you instantiate a high-level component. These cores are optimized and make designing for all the detailed functionality of things like the DCM or the PLL a lot easier. They also provide access to some very powerful design tools that can create common, sophisticated components at no additional charge. In summary, all slices contain 4 6-input LUTs and 8 registers. LUTs can perform any combinatorial function of up to 6 inputs or 2 functions of 5 inputs. 4 of the 8 registers can be used as flip-flops or latches. The remaining 4 can only be used as flip-flops. Flip-flops have active high clock-enabled inputs and active high synchronous or asynchronous set-reset inputs. Slice L slices also contain carry logic and the dedicated multiplexers. The MUX-F7 MUX combines the LUT outputs to create 8-input multiplexers. The MUX-F8 MUXes combine the MUX-F7 outputs to create a 16:1 multiplexer. The carry logic can be used to implement fast arithmetic functions. The LUTs and the slice M slices can also create shift register LUTs and be used as distributed memory. And finally, manage your control set usage to reduce the size and increase the speed of your FPGA design. Well, there is lots of useful information about inference and synthesis attributes in the Synthesis and Simulation Design Guide. This is available to you from the ISE software using its help menu or directly from support.xilinx.com. The XST User Guide provides very helpful coding recommendations that all Xilinx users should live by. It also includes a detailed description about all of XST's synthesis options. This information can also be found from the help menu. If you would like to see what other courses we offer or what other free RELs are available, go to the Xilinx Education link you see here. I would also like to mention again that there are architecture modules available that discuss the basics of Xilinx's newest devices. You may find this useful, especially if you want to learn more about the device differences. Again, my name is Frank Nelson. You've been listening to the Basic FPGA Architecture module for Virtex-6. Thanks for listening, and thanks for your business.